Okay, so first of course, first acknowledgement. So all the work that I am going to discuss is done by Shantanu, who will probably hear, and I acknowledge collaboration with our earlier PhD students Surojit, Chenyuan, and of course Subir. So we have some related work earlier, but this is something that we have been writing up. Okay, so basically this is going to be on quantum entanglement, just to sort of set the stage. So the idea is that we are thinking about some pure state, and the pure state is characterized by some entanglement entropy, which is defined by looking into some subsystem A with, let us say, linear dimension La. And what you do is you take this state of this pure state, and then you calculate the reduced density matrix. And so once you calculate the reduced density matrix, then in principle you can have an entropy, and so that entropy is characterized by this von Neumann entanglement entropy. For practical purposes, often we do not calculate von Neumann, we calculate this nth Renyi entropy, and a particular limit of this is the von Neumann entanglement entropy. For this talk, I will be only calculating the second Renyi entropy, which is sort of the easier things to calculate. So just to give an example, so if you calculate this object for in this so in this case, for let us say if you have this famous bell pair type states, and if you calculate let us say the entanglement entropy one of the qubits, then it will give this value. So if you use this formula, you will get log 2. So that is just the maximum this 2 qubit system can have. But the question is, all this of course we know are important in various quantum information and quantum technology resources, but why we are interested this about this in condensed matter physics. And the idea is that if we can calculate or measure entanglement entropy, it really characterizes particularly for pure states intrinsic quantum correlation. So generally whatever measurements you do, they have quantum correlation of course, but they have also a lot of other effects like classical correlations and things like that. So this is really intrinsic quantum correlation, and it can be used to characterize both very high energy states, high energy pure states, and also ground states, which are what I am going to talk about, like symmetry broken, critical and topological state. So what I am going to talk about specifically is this violation of entanglement area law. So typically if you have some gapped ground state in general dimension, let us say in dimension d, and if you do this calculation, what you will find is the scaling of this entanglement entropy with the size of the system goes like area of this system, which is L to the power d. So it should be La to the power d minus 1 in d dimension, and there are some corrections, subleading corrections, and these corrections often could be very important. For example, it can give some idea about topological order and other things, and even symmetry breaking. But what our interest here is about another type of features of entanglement entropy which appears for gapless systems. So for example, if you take one of the most well studied gapless system, which is some 1D gapless system, either boson or fermion, they are typically local theories described by some local conformal theory, and here a lot of things are known about entanglement entropy. For example, if you look at this nth Renyi entropy, then it follows this violation, which is the logarithmic violation of area law, and it specifically has this coefficient which is called the central charge, which is a property of this theory which is a kind of universal. And in this case, for example, a free fermion, a Luttinger liquid of this type, it is given by 1. I mean there are two conformal field theories, so in this case multiplied by 2. So it really characterizes the state. So you can essentially characterize ground state by this logarithmic violation, and the coefficient is universal. So now you can ask that what happens to higher dimension. Of course, if you have free fermions, you can do very efficient calculation and numerical calculation, and you can also argue, and what you can show that this kind of extends to higher dimension, that is area law in higher dimension again violated by this log L multiplicative factor with a coefficient which is also known if you know about the system. Now what about gapless interacting fermions, and of course here I am talking about something which is not a Luttinger liquid, that is a CFT, which I already discussed, which is known, but let us say our favorite thing, which is a Fermi liquid. So it turns out there are arguments saying that this Fermi liquid also should follow exactly the same behavior without any change even of the coefficient, this Widom coefficient. Okay, so it does not change, it is the same law, and you do not expect any renormalization of any of the coefficient even in a Fermi liquid. Of course, these explicit calculations are rare, there are some calculations. So, in some DMFT approximation we could verify this, but there are some other variational quantum Monte Carlo calculation. Now, one thing is that these results are all at 0 temperature. Of course, we strictly do not always measure thing at 0 temperature. So, you can ask that what happens to finite temperature, can you tell anything about finite temperature? Now, it turns out that at finite temperature none of these things that I mentioned earlier is a good measure of entanglement, they are not proper measure of entanglement. However, if you have this kind of gapless system that we are discussing, it turns out the fact that these are gapless excitations and they are low energy excitations, it is the same low energy degrees of freedom that controls both the behavior of entanglement at 0 temperature and low temperature thermodynamics at low but finite temperature. Okay. So, as a result, it turns out in CFT you have a very good understanding of this. So, this quantity if you calculate at finite temperature, what happens is this log L is modified by this factor here, and in this factor you get some thermal length which will come in my talk, a thermal length which is in this particular case is just given by the Fermi velocity which could be renormalized by interaction divided by pi t. So, this is a thermal length which diverges at t going to 0, okay. So, that 1 over this goes to 0, and you can see that this formula, if you take the system size much smaller than the thermal length, that is at 0 temperature, of course, system size will be smaller than the thermal length, then you will recover entanglement. Whereas, if your length, the subsystem size is greater than the thermal length, then you will recover thermal entropy, and what is interesting is that this same C appears here in both the cases. Okay. So, there is a crossover between entanglement and entropy. So, now what about Fermi liquid in general dimension? Again, it is believed that this formula just continue to hold even for Fermi liquids in higher dimension, you just extend the same way with the same coefficient. So, now the question is that what happens, sorry this is somewhat cut, but the question here is that, but what happens to this kind of strange metals, the kind of thing Anindo was talking in the morning in this hall. So, those kind of thing, and most famous example of course is what I think Subir is going to talk about is this famous ITC phase diagram, where and there are other examples like heavy fermions and all, but basically there is this strange metal state above here in the above optimal doping, and the main strange metallic feature is from arbitrary low temperature which you can access by let us say killing the superconductivity by magnetic field. You see there is a linearity behavior over a very large range, and instead of T square that you expect from a Fermi liquid. So, if you have, of course, we do not know exactly the theory of this system, there are of course many interesting proposals, but you can still ask that if there are some models of this non-Fermi liquids, this strange metal, you can ask similar question that can I characterize them by this scaling of entanglement entropy with subsystem size as we could do for Luttinger liquid or Fermi liquid. You can ask that is it still this same formula that there is a logarithm and then there is a coefficient, is the coefficient different, okay, from what we expect for a Fermi liquid. And another thing is often in this kind of strange metallic system there are some emergent bosonic degrees of freedom at low energies, and they are emerging out of the fermions themselves, but they are there in the low energy theory. So, you could ask that there are some kind of fermion boson entanglement in the theory apart in a fermionic system. So, what are the role of those? And what we are going to talk about is this model that Avishkar and Subir and many other collaborators have worked on extensively, and 2-dimensional Yukawa-Sachdev-Kitaev model, which has this critical Fermi surface, meaning it has a Fermi surface, sharp distinction between occupied and unoccupied part at 0 temperature, but it does not have a quasi-particle at the Fermi surface. So, this is called critical Fermi surfaces, and they are characterized by this kind of marginal Fermi liquid self energy and linear T resistivity, okay, somewhat like the phenomenology of these materials. So, what we are going to take is actually a 1D version of the model for technical reason I will just mention. So, these are called the 1D Yukawa-Sachdev-Kitaev model. So, let me describe the model. So, these models are basically some kind of large N model. Large N you can think of this model as some big atoms which are arranged on a lattice, or a quantum dot which are arranged on a lattice, and each lattice or the quantum dot actually have like n flavors. You can think of orbitals, let us say n orbitals, and there are both bosonic and fermionic orbitals, basically blue and black here, and these things are arranged on a lattice, in this case in 1D in our example, and the boson can hop and the fermion can hop. But they do not only hop, so these hoppings and these things are described by these parts of the model. There is some bosonic mass, but they do not only hop, this boson and fermion interact with a Yukawa coupling, which is a particular form. This Yukawa coupling is actually random, okay, and random in space. So, it is like a random Gaussian number, and it turns out that this randomness along with the fact that this I make this n very large can allow you to solve this model exactly, okay. And there are some spherical constraint in the model. This is sort of tune the phase diagram. So, there is a parameter gamma which will tune the phase diagram, but sort of the summary of this model basically gives you some critical Fermi points. So, now it is in 1D, so there is no Fermi surface, but there are Fermi points. These Fermi points are sharply defined because there is a distinction between occupied and unoccupied states, but there is no quasi particle at that point, and they are not also like Luttinger liquid. Okay, and the reason for taking this, as I will discuss, that this self energy is very strong at low frequency. It goes like square root of omega, which is stronger than omega log omega. So, it makes some of the non-Fermi liquid features more strong, and it is also numerically easier to calculate entanglement entropy. So, what I am going to now discuss is just very briefly, technical details apart. So, essentially what you do, like you have this quantum many body system, you try to calculate various things like Green's functions, which basically the self energy effects for both bosons and fermions, and here the important thing is this boson thermal mass, okay. And then there are also you can have order parameters. So, there are some equations, the exact large N equations that you can write, and these equations are somewhat complicated equation to solve, but if you can solve them, they exactly give a property of this very strongly correlated system. Okay, and what we are going to do is I am not going to discuss the exact steps of this, but we can solve these equations analytically at low energy at t equal to 0 for this parameter which will tune a quantum critical point, as I will show in the next plot. Basically what we will find is that gamma greater than gamma c greater than equal to gamma c, we can solve these equations by some low temperature expansion at low temperature, and we will do numerical solution. Okay, so let me first discuss the phase diagram. So, the phase diagram is actually characterized by this thermal mass. That thermal mass is calculated in this theory using some bosonic self energy, but important thing about this bosonic self energy is that it is actually a ohmic model of dissipation. So, there is a mod omega form in this self energy, and that kind of controls the phase diagram. So, this phase diagram as a function of this parameter gamma, the spherical constant, actually undergoes a quantum critical point, and in the left hand side of the quantum critical point, gamma less than gamma c, you have a 0 temperature order state even in one dimension, and this order parameter is only non-zero at 0 temperature, and on the right hand side you actually have, as I will show, a Fermi liquid phase where the mass of the boson is finite at 0 temperature. So, there is a finite mass even at 0 temperature, and then the mass grows as t square in the Fermi liquid regime. On the left hand side you have, in the finite temperature, again you have some kind of a non-Fermi liquid state, but we are not going to look at this in much detail. What we are going to look at is this quantum critical point where the mass vanishes, the 0 temperature mass vanishes approaching from this side. Okay, so, that is the quantum critical point, and in the quantum critical point there is a behavior, the mass vanishes at 0 temperature, but it behaves, m square behaves like linear t, it is like a strange metal, and you can sort of whatever I said, you can verify it numerically. You can actually calculate this, and you can see that there are this finite mass for gamma greater than gamma c, which goes to 0 at the critical point, and then there is some state here. Okay, and you can also calculate all these self energies in this model. You can basically show that the Fermi liquid has a self energy which you expect, it goes like omega square at low energy, numerically you verify. You go to the quantum critical point, you see that the quantum critical point has square root of omega self energy that is much stronger than the Fermi liquid, which has omega square at low frequency, and you can also verify that it is square root of omega, and there are some kind of state here which let me not discuss. Okay, so now what about the, so I said that the entanglement has some relation with the entropy. So, you can ask that what is the entropy in this system, thermal entropy, and again you can kind of calculate. So, it turns out that in this theory for whichever value of gamma, so the entropy has two contribution because there are fermions and bosons. So, there is a fermionic contribution, and the fermionic contribution is turns out is always given by the non-interacting value. It is completely renormalized by the interaction. Okay, it does not change the coefficient, the specific heat coefficient, everything is same as a non-interacting system. However, the effect comes for gamma greater than gamma c in the Fermi liquid phase. What you find that there is a bosonic contribution which is linear T for the entropy, and the bosonic contribution comes here because it is like a ohmic bath and it has a linear T coefficient which is determined by the self generated dissipation strength kappa. Okay. So, that is basically this disordered Fermi liquid phase over here, and you can also numerically calculate at the critical point. You find numerically we find that it is also linear T. So, just to summarize, the specific heat is linear T, however, the coefficient could be different from your non-interacting fermions because it has contribution from this bosonic degrees of freedom. Okay, so, basically this is what you get, the entropy is like that. So, now like a non-interacting electron it has a extra contribution. So, now you can ask that what is the effect of this to the crossover to entanglement. So, this extra contribution, does it appear in the entanglement, and if you imagine that there is some kind of again if you imagine that there is some type of behavior like I earlier showed, some thermal length, some effective central charge, etc., then of course, if you go to this limit where you get entanglement, which is the system subsystem size much smaller than the thermal length, then again you will get entanglement, and again if you go to the other limit you will get entropy. But now the question is that this entropy that appears here can have a contribution from the boson. As a result, this C effective can change. Okay. So, if you believe that there is a crossover because it is a gapless system. So, this is what we calculate, the entanglement entropy. So, what we calculate is basically again it is a 1D system, we divide into, so there is a periodic boundary condition, you divide into two parts A and B, but we calculate slightly peculiar object, is not exactly the entanglement entropy of subsystem, and this is for some technical reason. So, what you do, you basically trace out, so as I said you have to trace out from the density matrix some degrees of freedom. So, what we trace out is the boson and fermion in the B subsystem and also the bosons in the A subsystem. Okay, we trace out all of this and we look into only the fermionic subsystem entanglement or entropy. Okay. So, this is the quantity we calculate. Now, if you do this, now you see that there of course, there is this non-local effect that could be there like a bell pair, the long distance entanglement which is between A and degrees of freedom of A and B. But here because I have integrated out, I mean I have kept this integrated out these bosons here, there could be also a local entanglement between the fermion and boson, and that should appear in the theory. Okay, so, we use some method that we have been developing and also Rajdeep and other people are developing. So, if you want the detail you can look at these references. What happens is that in using this method essentially you turns out that you can again do a large N theory and it looks complicated, but this large N theory is now not the same large N theory, it is the large N theory for the entanglement entropy. Okay, and you need in this case turns out two replicas of the system, two entanglement replicas, and you again get set of large N equations, some complicated looking equations, but you can solve them. Okay. And you can ultimately calculate, just like you calculated the entropy, you can calculate from this theory the entanglement entropy or subsystem Renyi entropy, which at 0 temperature will become entanglement entropy. So, let me discuss the result of this. So, what I am showing here is basically the this fermionic subsystem entanglement entropy as a function of subsystem size at different temperature. Okay. So, starting from higher temperature to lower temperature, and you see that there is this different behavior. At very high temperature it looks linear, it is basically like entropy, and as you go to lower temperature you start seeing this entanglement contribution. Yes. So, now what you can do, it turns out that there is a kind of a universal scaling answer. You can collapse all the curves at different temperature and different subsystem size for a fixed system size L into a single curve, okay, a single universal curve that you can collapse into. And of course, you have to take some correction to scaling to collapse into this, but what two interesting thing appears from here. So, I mentioned to you about the thermal length, and I told you that the thermal length diverges at 0 temperature. What you find in this case, it does not diverge. Okay, it goes to a finite value at 0 temperature. There is a part which looks like A of AT, like inverse of that will diverge, but here this 1 over LT goes like AT plus B, okay, as if there is a intercept of this curve at 0 temperature. And it turns out that although there is no real reason, but it turns out as a effective description, this universal scaling curve you can actually form fit with a CFT formula which is shown here. Okay. So, since you can fit it, you have the universal curve which is irrespective of any assumed form, but once you have this universal scaling curve, you fit it and it fits with the known formula. However, with a L of t which is like this, okay, and you extract a C effective from the scaling ansatz and you find the C effective rather than being 1, it is 1.6, almost 60 times higher than what you expect for a Fermi liquid. Okay. And it turns out that from the same formula you can actually get different contributions. For example, if you take a particular limit, you show that this formula has two parts, there is one entropy, but there is one local entropy which is basically this fermion boson entanglement entropy which is there even if you kind of go to this limit, and in the other limit you again get two contribution, one logarithmic and another which is again this local entropy. So, all the crossover, the entropy, the local entropy and the long range Bell pair like entanglement, everything is captured by this same formula and the same universal scaling and such, and it turns out that it still works for Fermi liquid, but even Fermi liquid you get a larger value, and this could be because of this dissipative extra contribution that we had. And this is sort of the summary or kind of last slide that I have. So, you can plot the C effective as a function of distance from the critical point which is at 1, and you see that at the critical point the C effective is large, 60% larger, and even in a Fermi liquid it decreases, and we have done it for very large size, it almost goes to 1. And there is also this local fermion boson length scale, it is sort of the local fermion boson entangled length scale which again decreases as you go towards. So, if you go to very large value you should recover a Fermi liquid or basically a free Fermi gas, and so this is something I will skip, and with that let me conclude. So, what I tried to say that even for such strange metal, of course a model you can actually understand some kind of a universal scaling ansatz for the entanglement entropy, thermal entropy and local entropy, and what appears from this ansatz is that it seems that the non-Fermi liquids of this kind also has a log L behavior with a effective central charge which is larger than of course the non-interacting case, but there is this emergent bosonic degrees of freedom which also gives a fermion boson entanglement, and as I said, and we are right now calculating for the full subsystem, we will have it in some time scale. With that let me stop. No, that is okay, I am done.
Can I ask you to go back to the phase diagram?
Yeah. Maybe here also is there. Yeah.
So, the Fermi liquid is nothing liquid, is that?
No, it's in this case it is not. So, what happens is, I mean, okay, it's not, I mean basically it's like a disorder system, right. I have this SOIK disorder. So, it's not exactly a Luttinger liquid. The form of the propagator is not like Luttinger liquid. It has a, of course, there is a place the self energy matches with one of the K parameter, right, where omega square basically, but it's the form is different.
So, the rest of it is still the non-Fermi liquid is at finite temperature or just at zero?
This non-Fermi liquid starts from this strange metal and it goes up. So, here of course, there is a order state at 0 temperature.
So, order being gap state or gapless?
This is a gapless state. So, there is a order parameter like ON order parameter. So, this happens because you have kind of a long range coupling in the time direction because of this dissipation. So, even in 1D you have this T0 order state here. Yeah.
Final question, like, so the critical point you are studying, it's all disordered. So, everything, entanglement entropy and everything that you are computing are
It's disorder average, I did not mention. So, this theory is built such a way that you have to do disorder average to get all these results. But we disorder average properly, meaning it is the log of that thing is average. It is not that we average the some partition function or density matrix and then do this. Yeah.
Yeah, you are talking about the entanglement of fermions and bosons.
Yes.
So, in that scenario, how do you define the entangled state?
Yeah, so the entangled state again, I mean you have to, so these are of course, I mean you have the entangled fermion boson degrees of freedom. So ultimately you have, I mean in this theory at least you have some tensor product structure of the basis states, right. So you can sort of write the bosonic basis states and the fermionic basis states, and you can write the states. So since there is a tensor product structure, then you can integrate out one of them. So it's like because they are coupled, right. So ultimately you will create a, so let's say you have basis states of fermion and bosons which are unentangled, but when they form because of the Yukawa interaction, they will form a superposition, right, and that superposition has basically entanglement, but you can't sort of draw a picture like a one fermion one boson pair here, because it's like a soup of this strongly interacting metallic state in thermodynamic limit.
Is there any experimental counterpart of this?
The measurement of entanglement, no, not in this system.
So, when you are writing the C effective in the central cell, I understand it as the coefficient of the log.
It's not, yeah, I should say I'm not calling it some, it's just a C effective.
It's just a
Yeah,
coefficient.
yeah,
It's
yeah.
not like there's a
No, there is no, yeah.
Any other questions, comments? So just following up on that,
Right.
So one should understand is the same sense as the strong disorder as such a fixed point, so the critical point. Is that analogous?
No, this one is not. This critical point is just dissipative Owen model, critical point. I mean, of course, there are these fermions. If you look at the fermions, they have also this strange metallic behavior, and it's a self-consistent dissipation, but it's not RSRG, no. Yeah. Because of the large n limit.
All right, so let's thank
Yeah,
Sivan
thanks.
once again. So the next speaker is Professor Vasudev Silugudi.